We're going to work this problem here, which is a sequence or a series of ropes. We have a wall here and a wall here, or a segment of rope connected as such, and there's a mass M that's hanging below. And so we're given a lot of information. We know the angle here is 30 degrees, the angle here is 30 degrees. We have a little triangle information that ultimately will tell us the angle this is, and segment AB is horizontal. So it tells us all ropes can take 100 newtons before breaking. What is the maximum mass of this box M that's hanging there? So the critical piece of information is that all of these ropes can take 100 newtons before snapping. So ultimately what we're going to do is similar to what we've done in the past. We're going to write our free body diagram down, and then we're going to write our equations down. And then we're going to find out that it's difficult to solve all of these equations because we don't know what this mass is. That's what we're trying to find. And we're going to have all of these tensions everywhere that's going to be unknown as well. However, we know that all of the ropes can take 100 newtons before they break. So basically what it's going to boil down to is figuring out which one of these ropes is going to break first. That's going to give us the constraint we need to solve for all of the tensions here. So I'm going to solve it my way. It's the way that popped out for me. You might look at this and see a different way to solve it yourself. That's fine, as long as you get the right answer. No one's going to have a problem with that. So we look at this and we draw a free body diagram. Immediately it becomes cumbersome because we have intersection points, two different intersection points. Now you could try to make this one large area to study, but I'm going to choose to write two different free body diagrams, one at this intersection and one at this intersection. Of course they're connected by the same piece of rope, so we're going to have a common tension there. So basically the free body diagram for point B is going to look something like this. We're going to have point B right here, and then we're going to have a tension going up like this. We're going to call this FBC because it's going from B to C. And then we're going to have a horizontal tension right here. We'll call that FAB. And when you're doing these problems, you can label them T for tension. I like to use F for force. It's really all the same thing. And then we'll have down here, the mass is pulling, so there'll be a tension pulling down more or less roughly like this, and this will be FBE. Okay. Now, one more thing I want to add before we go any farther is notice this is 30 degrees, so I'll just kind of add this here. This is 30 degrees. All right. Now that is that one. Let's move over to the other one here and put a dot here and say that this is point E. Now, looking from the point of view of point E, there's a tension that goes off in this direction. F, we'll call it DE. Right? And then we have the weight, of course, coming down. We don't know what that is, but that's what we're solving for. And then we have a force going off this direction, which is from this guy right here. We'll try to make that a little bit steeper. We'll call that FBE. Notice that this FBE right here is really the same one that's essentially connected to this one here. We're drawing them separated. Ultimately, these two will appear in separate equations and could possibly be eliminated, but we'll do that, later down the road. Now, also notice that this angle right here is 30 degrees. So we'll go ahead and label everything we know. Now we first start looking at this and saying, what can we find from this? We could write our equations, but if you try to write the equations right now, you're going to run into a problem because you're not going to be able to find the components of this acting horizontally and vertically because we haven't put an angle there. We want to use this information to find the angle of this line. So if we can kind of imagine, if we look over here, if we can kind of imagine a dotted line going this way, what I'm trying to say is what would be this angle here? And this kind of forms a triangle, and you see this matches up exactly with what the triangle is here. So this angle theta, as I've drawn it, is really exactly the same as this angle inside of there. So if I want to do this out of the way to not clutter up this stuff here, I'll just find what this angle is here. And if you look, the tangent of this angle, if you look inside this triangle, is the opposite over the adjacent hypotenuse, or I should say the adjacent side. So it's 4 over 3, 4 over 3. All right, and so when you take 4/3 and you divide that and you take the inverse tangent, theta is 53.13 degrees. So this is 53.13 degrees. So basically this angle here is 53.13 degrees. And if you look, here's a horizontal line, here's a horizontal line. These are alternate angles here. So from your geometry, this is also 53.13 degrees. And that is the angle we really want to help find our sines and cosines. Now, if this is 53.13 degrees, then that is going to be exactly the same as this angle here, 53.13 degrees, because this line is connected to this line if you kind of look at the way I've drawn it here. And again, this would be an alternate interior angle from this. In fact, this angle here that I've drawn is really the same angle as this. So now we have everything we need because we use the drawing to find the extra angle that we have. We have the angle for each of these vectors' directions, and of course this is horizontal and vertical. All right, now what we want to do is work in the x direction for this guy here. So we'll call it x direction, and we want to write an equation in the x direction. Now, this is purely in the x direction, so it's negative FAB, because it's pointing to the left. And then we're going to add to that FBC cosine 30, FBC cosine 30, and then we're going to add to that this one here, FBE cosine of this, FBE cosine 53.13, and that's equal to 0. All right, and then over here for the y direction on this guy, the y direction on this guy, this doesn't participate. This guy, the y direction pointed up is FBC sine 30, FBC sine of 30. And then we subtract, because this is pointed down, FBE sine of 53.13 degrees, and that's equal to 0. Okay? Because these are the only guys acting in the vertical direction. Now, I don't have room on the right-hand side to write these equations, so I'm going to write them underneath. Try my best not to get too cumbersome. So the x direction for the right-hand drawing, this x direction over here, FBE cosine 53, which is negative because it points left, FBE cosine 53.13, that points to the left. This guy is positive FDE cosine 30. And that's going to equal 0 because this is left, this is right, and that's everything there. And then it is equal to 0. And then finally, let me switch colors here. For the y direction, see if I can wedge it in down here, I have FBE sine 53. So FBE sine 53.13, and that's pointed up, so it's positive, plus this one, FDE sine 30, FDE sine 30, FDE sine 30, pointed up, of course, so it's positive, minus the weight because it points down, minus the weight is equal to 0. All right, so we've done quite a bit of work. We have an x direction and a y direction for this one, and an x direction and a y direction for this one. Now, I'm going to label these equations. Equation number 1, equation number 2, equation number 3, and equation number 4, because we're going to use them a lot. And instead of writing the things over and over again, it'll be easy to reference it. So basically, your problem boils down to solving the system of equations. If you could somehow do that, then you would have everything. You would know everything about the system. All of the tensions, forces, and of course the unknown weight is what you're solving for. And that's there too. Unfortunately, you can't solve for it because you actually have 4 equations, and if you count them, you have 5 unknowns. If you go through here, 1, 2, 3, and then this will be 4 and 5 is the weight. So you can't really solve the system of equations straight away. What is the additional information, the piece of information you need to solve the system? The additional piece of information is given to you right here. All ropes can take 100 newtons before breaking. So really, you have all of these forces listed as tensions, basically, in here. But the problem is you don't know which one's going to break. Eventually, you're going to put a heavier and heavier and heavier mass here, pulling and pulling and pulling. One of these pieces of rope is going to break first. That one is going to reach its 100 Newton breaking point first. So if you could just have a crystal ball and figure out which one of those is going to hit 100 newtons first, then you just put that value of 100 newtons into the equations, and then you lock down your variables because you have enough equations to solve everything that remains. So the question is, what's it going to be? This segment, this segment, this segment, or this segment? You've got 4 to choose from. It's very difficult to just do that. Now, I can say that if you wanted to brute force it, you could choose this segment breaking first and solve the system. You could choose this one and this one. You could do them all 5 times and see which one is going to yield answers that make sense, okay? But that's a little bit cumbersome. So what we can do is look at you can really stare at this and look at it so many different ways, but what I'm going to do is encourage you to look at equation number 3. Basically, we're going to examine these equations and try to deduce which of these is most likely to be the one that's going to stress first. So let's look at equation 3 for a second. I'm going to write this one over here. Negative FBE times cosine 53.13 plus FDE cosine 30 equals 0. So this is one of the equations here. What you need to do is try to work with it and see what you can learn from it. So let's go ahead and do that. This will be negative FBE cosine 53.13 is 0.60 plus FDE cosine 30 is 0.866, and that's equal to 0. So basically, to cut to the chase, I mean, I can do a bunch of algebraic steps. But basically, if I solve this for FBE, what's going to happen is I pull this over here. Of course, it's going to become negative when I do that. And then I divide by 0.6, negative 0.6. So I'm going to have the division of this and this. Then what you're going to get on the right-hand side is 1.44 FDE. What does this equation say? Basically, I take one of the equations, I solve for this. What does this say? What it means is that no matter what the tension or the force inside of segment DE is, BE is always going to be bigger. Now think about that for a second. Whatever the tension is that you surmise is in here, whatever you measure is in this rope, the one in segment BE is always going to be bigger. So what it's saying is when you compare DE, which is this one, to BE, which is this one, BE is always going to have a higher tension in it than this one by a pretty wide margin. And you might guess that because this one is more steep here, and it's probably bearing more of the weight from this block anyway. So if you wanted to pick which one of these two, just forget about the rest of them, which one of these two is going to break first, this is the one that's going to break first of those two. Okay, so you can play a little bit of king of the hill here and go around and do little examinations like this and figure out, okay, which one's going to win out of these two. And right now you figured out that basically this one will fail first. But only because we've only compared these two. It doesn't mean that this is the ultimate one that's going to break the most. What it means is comparing this one and this one will win. So for right now, let's make the assumption that FBE, this one, is going to fail first. So we could run our analysis through and solve everything making that assumption, but it might be fruitful to go ahead and compare a different one. So we will use equation 2, this one, to compare BC and BE. Notice that we've already said we think BE is the king of the hill of these two, but this equation compares BC and BE. So let's go ahead and do that. FBC sine of 30 minus FBE times the sine of 53.13 is equal to 0. And again, I'll spare you the details here. Whenever what we're going to solve for, we already know that BE is going to be bigger than this guy. So let's solve for FBC, okay? And what's going to happen is we're going to move this to the right-hand side and we'll divide by sine of 30, which is 1/2, so that'll get divided. So it'll be this divided by the sine of this. What you're going to get on the right-hand side, 1.60 times FBE. Now notice what we've figured out here is that when we compare BE to BC, BC is always the one that's going to break first before BE does. Because no matter what the force of the tension is in this rope here, this one's always going to be bigger. So as you add more and more weight, you can see which one's going to break first of everything we have here on the board. Notice BE is here and here. So what we basically figured out is our original king of the hill was this one because we compared these two and said this one's going to fail first. But now we're comparing this one to BE and we figure out that this one will actually break first. So let's erase our little arrow and we basically say, well, we don't think that one's going to break first anymore. So then we're going to say this one's actually the one that's going to fail first of everything we have on the board. So we've done a kind of back of the envelope analysis of BE, which is this segment, of DE, which is this segment, all right? and of BC, which is this segment. And if everything that we have on the board, it looks like this one is actually going to be the one that failed first. The only thing that we haven't actually looked at is this other segment over here. But of everything on the right-hand side, it looks like this is going to reach its breaking point first. So let's just do one quick check and see, compare it to this guy, and then we will know what to do. Well, how do we do that? So we go look for an equation that involves A and B. So we look around, we see the first equation fits the bill. This involves AB. So let me rewrite this guy over here. Notice it's negative FAB, so we'll move it to the other side of the equal sign and just say FAB is equal to FBC cosine 30. I'm just basically writing FBE cosine 53.13. I'm basically rewriting equation 1. I just put FAB on the other side of the equal sign. So of everything else, all the other ropes, BC is the one that fails first, okay? More than BE, more than DE. But now we solve for AB, and we see that on the right-hand side, it's going to be BC times a number, and then it's also going to be BE times a number. So basically, FAB is going to be the sum of the two highest tensions that we have on the right-hand side. There's some decimals, okay, of course, multiplying together, but there's no subtraction here. These are additions. So basically, this guy right here is taking a huge tension because it's taking some fraction of the tension from here and some fraction of the tension from here. And it's adding them together because it's physically connected to this guy here. So we can't be 100% certain, but our intuition is telling us is that even though there's some decimals here, since this is added together and since these are high tension ropes anyway, that it's likely, at least very possible, that the tension in AB is actually going to be the one to reach its breaking point first. And then when you step back with that analysis and look at it, it kind of makes sense to you. I mean, the weight is here, there's some tension here and here, but this one is the only single line connecting it to the wall here. So in a way, it's basically bearing a huge brunt of the force because it's connected to everything else on the right-hand side. So now, because of this, we're going to guess, and you won't know until the problem is really totally done, we're going to guess that actually AB is going to fail first. We're going to guess that AB is actually going to be the one that's going to fail first. Okay? So what you do is then you say, all right, if this is true, let me rewrite this equation. Let me rewrite this equation. This right here is FBC times cosine of 30, and cosine of 30 is 0.866. Okay? Let me go ahead and put this, make this a little bit clearer. BC times this. And then we're going to add to this, cosine 53.13 is 0.60 FBE, like this. And then FAB, we're going to put on the right-hand side, we're going to say that it fails first, so it reaches the 100 Newton tension first. All right? Now, we want to basically solve the system, so we have an equation with FBC and FBE, and we go back and look, okay, to equation 2 right here. This is another equation in FBC and FBE. All right, FBC and FBE. So we have two equations and two unknowns we can solve. So we put this guy directly underneath here, and if you go back and look, basically it's this equation here that we just did. So what you're going to have here, sine of 30 is 1/2, so this is going to be 1/2 FBC. And this will be minus sine of 53.13 is 0.80 FBE, and this is equal to 0. Basically, now that we've got our constraint in place, we found another equation with these two variables. We eliminate all the cosines and stuff, put numbers in their place, and now you have two equations and two unknowns. So you can dump this into a calculator to figure out, or any kind of solver, to figure out what these two things are, and what you find out is FBC is 80.58 newtons, and you find out that FBE is 50.36 newtons. Now these are important, so I'll asterisk them. Not what we really need to solve the problem completely, but they're very important because we're making our way into the final solution. So we have the two guys here. Notice that all of these ropes break at 100 newtons. And because we made this assumption, both of these tensions in these ropes are both less than 100 newtons. If we had ever gotten a solution where one of them was more than 100, then we would know that we made an incorrect assumption or made a mistake along the way. So how do we finish with the analysis here? So we have this guy, and basically we want to go down here and end up finding the weight. We know what FBE is, we just found that, but we don't know what FDE is. So let's go up and see if we can figure out FDE. We can do that from equation 3. So let me go over here, and let me go put equation 3 down on the board. So we'll have negative FBC cosine 53.13 plus FDE cosine 30, and that's equal to 0. And basically, we know what FBC is now. We just found that it's 80.58 cosine of 53, 0.60, plus FDE is multiplied by cosine of 30, which is 0.866, and that's equal to 0. So when you multiply these together and you move it over and you divide by this, you get FDE is 34.89 newtons. And notice that this is also less than 100, so we haven't broken any major rule of the problem because that's less than 100 as well. So now we go down to equation 4, because the equation 4 is the only one that deals with the weight. But now we know this, and now we know this. So we can find the weight, which is exactly what the problem actually asked us to do in the first place. So from equation 4, we have FBE sine 53.13 plus FDE sine 30 minus the weight, and that's equal to 0. So FBE, we just calculated 50.36, sine of 53.13, 0.80, plus FDE, which we just found here, 34.89, sine of 30 is 1/2, and that's equal to the weight. We'll just move that over to the right-hand side. And so the weight in newtons of this guy, you multiply, you add, you get 57.73 newtons, but actually that's not what we were asked. They didn't ask for the weight. We want to know the mass of the box. The weight is the mass times gravity. So 57.73 is equal to the mass times 9.81 meters per second. And when you take this and you divide by 9.81, what you get is 5.89, and the units of mass is kilograms. So basically this box can be a maximum of 5.89 kilograms before one of these ropes breaks. And the entire challenge of the problem was really just figuring out which one of these guys is going to break first. And it's really impossible. I mean, you could kind of guess with intuition it might be this one, but it's impossible to know for sure without really doing some math and thinking about it. So what we did is we drew two free body diagrams, one at this point and one at this point. We had to do some trig to figure out what this angle was here, but then we wrote an x equation for this and a y equation for this, and then we wrote an x equation for this and a y equation for this, and we have 4 equations. We have too many unknowns to really solve for, so we have to figure out which one of these ropes is going to break first. So we start going down the line. We compare with one of the equations down there. We compare BE and DE and figure out BE is going to break first. And then we use a separate equation to compare BC to BE and find out that BC would actually break before any of the other ones that we've studied so far. And then we use yet another equation to figure out that AB, being a linear combination or sum of these two guys, which are the other previous kings of the hill, we make an educated guess and say that this is probably going to be the one that fails first. So then we take this equation, which is right here, we write it down, making the cosines go away and just put the numbers in place, and then we basically say that FAB is 100. We say that it reaches 100 newtons first. We go hunting for another equation over there that involves these same two variables, which is really this equation right here. We, again, convert the trigonometric stuff to numbers. Basically, I'm trying to put it in a form for you that you could dump it into a calculator solver or use a matrix. This allows us to find two of the tensions right away. Then we go grab another equation that involves dE to solve for this one. We just plug in what we just found to find that one. And then equation number 4 is the only one involving weight. You know that you're going to end up using that equation anyway eventually because you're trying to find the weight. You plug in what you know and you figure out the weight, and then from that you can find the mass. Definitely not something that you could look at and say, yeah, I know I have a path to the answer right there. I mean, you have to take it one step at a time. Write your free body diagrams, write your equations, and then make your assumptions. Now, if we had screwed up along the way and picked another rope or another piece of cable that would have reached 100 newtons first, and if we had done that in error, then once we had solved everything, undoubtedly what would have happened is we would have figured out the tension in one of the other ropes was probably going to be more than 100 newtons, and that would violate the constraint. So if you make an incorrect assumption like that, then you're going to catch yourself when you get to the answer stage. So we try to do as much front-loaded work as we can so that we don't have to continue solving the problem over and over and over again. You're going to make mistakes, but we try to make the best educated guesses that we can. So that about does it for 2D particle equilibrium. All of these problems have been in 2 dimensions. Now what we'd like to do is go on and work on some equilibrium problems in 3 dimensions and show you how to handle it when we have a little more complexity of 3-dimensional space. Learn anything at mathandscience.com.